Alrighty, and we are back. So let's knock out the homework from the previous section so that we can finish up 4.1 finally. So let's see, we had to start off number 3 from 4.1. And for that one, we are given y is equal to, let me move some things around to make it easier to see what I'm doing here. Y is equal to c1x plus c2 x natural log of x. And we're given an interval from 0 to infinity. And let's see, our differential equation is x squared y double prime minus x y prime plus y equals 0. And we have the conditions of y at 1 equals 3 and y prime at 1 equals negative 1. Okay, so our goal is to figure out what the C1 and C2 are. So we'll start off. We're going to first take this y is equal to C1 plus C2 times all of this and take the derivative of that. So if I do that, I'm going to get y prime is equal to, well, we're just going to have C1 plus C2 times, here we go, first times derivative of the second, x times 1 over x, plus the second, natural log of x, times the derivative of the first, which is 1. So there we go. Alrighty. So if I rewrite this, I can get y prime is equal to c1 plus c2 plus c2 natural log of x. Okay? Okay, so now let's see if we can figure out what we have here. So that's all I need to plug in my initial conditions. I'll start off with my y expression. So I plug in, I've got y at x equals 1 is equal to 3. So 3 is equal to c1x plus c2. Oops, I forgot. Already that makes a 0, isn't it? Hold on. Holy cow, it's a John eraser. Hold on. That's not the eraser that I wanted to use. Okay, we'll just pretend I meant to do that. So 3 is equal to, well, I already know that it's going to be c1 times x, right? And so my x in this case is 1, so that's just c1. And then plus, I've got c2 times x times natural log of x. So it's going to be c2 times 1 times the natural log of 1, which is 0. So this term drops. So we're left with 3 is equal to c1. So I know what c1 is now. So now I can plug in my next condition, the y prime condition, into this expression. And so y is negative 1, and that equals c1, which is 3, plus, I'm going to have c2 plus c2 times natural log of x. Well, we already know that that's going to be 0, so I can just go ahead and erase this. So c2 is going to equal, when the dust settles, negative 4, right? Okay, so my solution is y equals 3x, well, that's my c1, plus, or rather minus, let me just do it that way, minus 4x natural log x. And there you go. That was number 3 in a nutshell. So it's just kind of a refresher of how we solve for our constants to get our particular solution. Not too bad. So let's move on to the next one. Clear this. Alrighty. So this one is way more fun because for this one, we have boundary values. We have boundary conditions. So we have y is equal to c1 e to the x cosine x and plus c2. Can you guess? Yep, e to the x sine x. Isn't that beautiful? There's usually that symmetry just kind of hanging around. Now we are given that the differential equation is y double prime minus 2y prime plus 2y equals 0. Okay, so that's what we're going to use for everything that follows A, B, C, and D. So we're going to start off with A, and our boundary conditions are going to be, let's see, we have y at 0 equals 1, and, oh, sorry, these look like, that's interesting. Oh, let me check the book, because that does not look right. They really have the prime in there? He does have a prime in there for the very first one. Surely they don't mean that to be a prime. That would be, I mean, it would work, but that's kind of mean. Let me look that up. I know this is like dead air and you're loving me looking this up, but that is kind of odd. So this is number 13. Oh, it did. Want you to do that. Okay. Well, that prime is legit. That just looked very strange. So, all right. And I'm all tangled up now, of course, because I just spun my chair around. Here we go. All right. So y at 0 is 1, and y prime at pi is 0. Okay. So I need to know my y prime expression, because I'm going to have to use it for this one. So y prime is going to equal, well, what do I have here? I'm going to have a lot of stuff. So here we go. C1 times product rule first, e to the x, times derivative of the second, negative sine x, plus second, cosine x, times derivative of the first, which is just e to the x. So just looks like that. And really, I could just put this negative sign out in front of here and just erase it here. That way it'll look a little bit better. Alrighty, so that's C1 plus C2 times is going to be pretty much the same thing. We're going to wind up with e to the x cosine x, and then plus e to the x sine x. Okay, so there we go. That's our y prime. Let's start off with the just plain old y though. So at x equals 0, y is 1. So I'll plug a 1 in here, and I'm going to get C1 times, well, e to the x is e to the 0, which is a 1, times cosine at 0, which is a 1. And then same thing is going to be for the C2, except they're both, the sine x is going to wipe out both of them. We're just going to have C2 not equals plus C2 1 0, which makes this whole thing 0. So I just wind up with C1 equals to 1. Not bad. So I've got the first one. Now, let's see. I'm going to plug in my x is pi, y prime is 0, so I'm going to plug it into this equation right here. So I get 0 is equal to C1 times, well, let's see, I've got negative e to the pi times sine of pi. But what is sine pi? Well, sine of pi, if you look at your unit circle, where's pi? Pi is over here. What is the y value there? That is a 0. So this whole term is going to go to a 0. And then I'm going to have plus e to the pi times 1. Okay, so that takes care of that. Alrighty, and then I'm going to have plus C2. Erase this. Should have kept my giant eraser way faster than this. Alrighty, C2 times, it's going to be the same kind of thing. I'm going to have e to the pi times 1 plus 0. Now, my C2 is going to, my C1 is 1. So this winds up 0 is equal to e to the pi plus c2 e to the pi. Okay? And so I'm going to move e to the pi over, divide out. I'm going to wind up with c2 is equal to negative 1. So I'm going to wind up with a solution of y equals e to the x cosine x minus e to the x sine x. And there you go. That'll do it right there. So is that all that we had to do for that one? Looking at it, I think that looks pretty good. Alrighty, so any questions on that? Not too bad. Did we have to tell if there were multiple, single, or I can't remember. No. So for this one, let's see. Alrighty. Determine whether a member of the family can be found that satisfies the boundary conditions. Oh, we just want to know if it works or not. Okay. If it's a contradiction or something like that, we can do that. Alrighty. So now we can move to the next one. And so that one right there is one where we had a single solution for those boundary conditions, just to clarify. So let's move to the next one, which is going to be part B, and I want to rewrite the stuff at the top each time. Wait, no, I don't. Hold on. Bear with me. I'm about to do something crazy and awesome. Here we go. I'm going to change that into a monster eraser. That way I can keep everything. So here we go. Part B. Oh, yes. That is insanely satisfying to wipe out that much text all at once. Okay, here we go. Now I put it back to something that resembles normalcy before I move to B. So part B, we had y at 0 is equal to 1, and y at pi is equal to negative 1. Okay, so we're going to do exactly what we did, except now we just have to worry about y. We don't have to worry about finding the derivative. So start off with the first one. So when x is 0, y is 1. So 1 is equal to c1. Well, we've already done this, haven't we? That's c1 is equal to 1. Okay, that's not bad. Now let's move to the next one. So this one is y at pi is negative 1. So if I come up here and put a negative 1 is equal to c1, which is 1, times e to the pi times cosine pi, which is negative 1. That's the x value at pi, so that's negative 1, plus c2 times e to the pi times sine of pi, which is, yes, again, that's 0. That's gone. So I'll wind up with, well, I wind up with not much. C2 is gone. So, in other words, this has no solution. Those boundary conditions are bogus. They are not going to give us anything we can work with. So, moving on. We can now go to part C. So, part C, let's see what we have. Let me erase this with the giant brush of erasing. Oh, that is so cool. Just have to be careful with that so I don't knock the top stuff up. Alrighty, so now let's do C. Y'all have no idea how happy that makes me that I can do that. So C1 is equal to 1, and wait, I gotta do my boundary conditions. I've already jumped the gun. I was looking at that going, hey, well, C1's obviously 1 again, but let me write down the boundary conditions first. So we have y at 0 equals 1. That's why it was jumping ahead. And then y at pi over 2, so new boundary here, is equal to 1. Okay, so C1 equals 1. We already know that. So now I can go straight into finding this one. So 1 is equal to 1 times e to the pi over 2 times cosine of pi over 2, which is 0, gone. And then plus c2 times e to the pi over 2 times, what is sine of pi over 2? 1. So what do I get? I get something kind of strange. I get, if I look at this, I can divide both sides by e to the pi over 2. And when I do that, I'm going to get c2 is equal to e to the negative pi over 2. And if you want to see it in a little bit of detail, I've got 1 is equal to e to the pi over 2, c2, divide both sides by e to the pi over 2, and that's how I get e to the negative pi over 2. Alrighty, so if that's the case, I wind up with y is equal to, got one of my cats coming to say hello. We've got c1 is 1, so it's going to be e to the x cosine x, and then plus c2, which is going to be plus e to the negative pi over 2 times e to the x. Don't get on my laptop. Nope. Thank you. Sine x. And there you go. That right there is the solution, and this is a single solution. So far so good. Now let's clear it. Alright, and for D, we have, let's see, boundary conditions are y at 0, new condition is 0, well that's new, and y at pi is 0. Okay? So let's start with this one. 0 equals c1 times 1 times 1. And then we already said that's 0, so c1 is now going to equal 0. Okay, now I can move to the second boundary. I've got 0 equals, c1 is gone, is a 0, so this whole term is gone, plus c2 times e to the 0, which is 1, times sine of pi, which is 0. So I'll wind up with 0 equals 0. Now, that is the solution no matter what value I put in for C2. I can make C2 equal to 1. I can make C2 equal to negative 937. I can make C2 equal to cat. It doesn't matter. It's still going to hold. Therefore, this one, C2, is completely arbitrary, and there are an infinite number of solutions. So, many solutions. And there we go. Not too bad. Those were fun. Alrighty, let me clear screen. We will go to the next set, which I really, really like. So here we go. If I can clear the screen. Okay, so now let's go to 15. I like the next three problems a lot because I get to do the Wronskian. So we have three equations. We're given f1 of x is equal to x, f2 of x is equal to x squared. I shouldn't call them equations. These are actually solutions that we've been given. And f3 of x is equal to 4x minus 3x squared. Too much time in algebra land. I'm going to blame that. Alright, so I have these solutions, and I want to see if they are linearly independent. Now, the Wronskian will always work. Like, always. But I'm going to show you a better way in some cases right after I finish this. So the way you line up the Wronskian is you line up your three solutions. 4x, that's 3x squared. Okay, and then you take the derivatives of each one of the functions below. So 1, 2x, 4 minus 6x, and then 0, 2, negative 6. Okay? So now we're going to take the determinant of this. So let's see, we're going to have x. This, I don't know if you've, it may have been a while since you've done, the determinant of a 3 by 3. But it's going to be x times this little subdeterminant, which is going to be negative 12x. This times this, minus this times this. Minus 8 plus 12x. Okay? That's for the first one. And now I got to put my eraser on a really small level so I don't erase anything important, because I'm not going to be doing this one for the next one. The next one is going to use the middle term. And the middle term always, oh gosh, that's a lot of work. I may just do it in different colors next time. Golly, that's a lot of work to erase all that. Alrighty, so moving on. You subtract the middle one, so minus x squared times the subdeterminant. Well, now the subdeterminant is going to be, I'm going to use a different color. So it's going to be this term times the little subdeterminant given by these guys. So I'm going to have 1 times negative 6, so negative 6, minus this times this. Well, this times this is 0, so I can just close up right there. And then plus the last one is going to be, whoops, let me take that, I almost wrote that down wrong. 4x minus 3x squared times, now it's the subdeterminant of, so this one times the subdeterminant of this one. So I'm going to get 2 minus 0, so just 2. Oops. Don't want to do that. That's going to look weird. Alrighty, go back to the right color. 2. There we go. Okay, so now what do we get? Well, we get negative 12x and positive 12x are gone, so I'm going to get negative 8x, and then plus 6x squared, plus 8x, minus 6x squared. Cancel, 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 cancel. Equals 0. So are there any values of x that would make that equal to 0? I can think of a few that might work for that. So these are definitely dependent. So these up here, these solutions are linearly dependent because the Wronskian was equal to 0 for at least one x. In our case, for every x. Dependent. Okay. Now, what is the simple way that I alluded to earlier? Well, if you'll allow me to erase, here we go, John Eraser again. Wahahaha. Oh, that was nice. All right. I think I'm going to start doing that in general. That's just way more satisfying than just clearing the screen would be. Alrighty. So, one of the properties of linearly dependent solutions is you can form one of the solutions by making a linear combo of the others. Okay, what in the world am I talking about? Well, I note that this third solution here is made up of x's and x squares, and my other functions happen to be x and x squared. So I could say just that f3 of x is equal to 4 times f1 of x minus 3 times f2 of x. That is the quick check to see if something is linearly independent or dependent. If you can form one of the solutions out of a linear combination of the others, and what I mean by linear combination, you can put a coefficient of any kind in front of the others and add them together, and it will make the third one. So if you can do that, they're dependent. Dependent. Alrighty? So, ready to move to the next one? Alrighty, so let's clear this. 17. So, or was it 17? No, I didn't do 17, I did 19. 19, here we go. So f1 of x is x, and f2 of x is x minus 1, and f3 of x is equal to x plus 3. Alrighty? So far it looks kind of odd, like, is there a way I can form a linear combination here? Actually, there is. Do you mind if I do that first? How can I make, let's say I'm trying to put together f3. How do I get x plus 3 out of some combination of these? Well, that's not too bad, is it? All I have to do is get that 3 by doing minus 3 f2 of x, right? Well, if I have minus 3 f2 of x, it's going to give me a negative 3x. How do I get positive x? Well, I just add 4 of f1 of x. If I do that, I'm going to get 4x minus 3x plus 3, which winds up x plus 3. Isn't that cool? That equals f3 of x. So they are definitely linearly dependent. But if we wanted to do the Wronskian, we'll do a quick one, because this is cake to do. We've got x minus 1. You can already probably see what's going to happen. X plus 3. 1, 1, 1, 0, 0, 0. That determinant is 0 right off the bat, because every time I do the little submatrix, I'm going to wind up, or subdeterminant, I'm going to wind up with a 0. So that's definitely linearly dependent. Alrighty? So now we can move to the last one. The last one was number 21, I think it was. So 21, we had f1 of x is equal to 1 plus x. f2 of x is equal to x. And f3 of x is equal to x squared. There is no way I can do a linear combination of f1 and f2 to get f3. It's not happening. So let's just verify that by looking at the Wronskian. So I'm going to have 1 plus x, x, and x squared. Okay? So I'm going to wind up with 1, 1, 2x, 0, 0, 2. Okay? So I'm going to start off with 1 plus x times 2 minus x times, it's going to be this 2. Nice, it kind of worked out that way. And then finally, plus x squared times 0. So this one's gone. So what am I left with? I'm left with 2 plus 2x minus 2x. These cancel. I'm left with 2. No matter what value I make x, this is never going to equal 0. Therefore, they are linearly independent. And there you go. The Wronskian is the fallback on whether or not something is linearly independent. As a rule, if I'm trying to tell like multiple solutions are linearly independent, first thing I do is just kind of give them a once over and just look to see if I can combine them in a way that will make the third. If I can, I don't have to do the Wronskian. It's already dependent. But if they can't, well, then if I can't see the way to do that, then I just go ahead and run the Wronskian to verify that they're linearly independent. So there you have it. All right, now we can move into theory. So let's get back to the fun stuff. All righty. Okay, so let's tackle some of this theory. We're going to start off, and I warned you in advance, we're going deep into some of the theory here, so I know you love it. Here we go. If we have y1, y2, comma, dot, 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 all the way down to y sub n, are n linearly independent solutions of the homogeneous, here we go, linear nth order dE on some interval I, then y1, y2, all the way to y sub n are said to be, drumroll, a fundamental set of solutions. Okay, so if I have an nth order homogeneous, what does homogeneous mean in this case? It means that it's the differential equation is going to be equal to 0, right? Homogeneous is equal to the g of x or f of x or whatever you want to call it after the equal sign is 0. Non-homogeneous, it's not. So homogeneous, linear, we know what that means, nth order. So if it's the nth order, it's going to have n solutions, which we're going to call y1, y2, all the way out to y sub n. If they are linearly independent, then they are said to be the fundamental set of solutions. Okay? So basically, we can use this definition to do some other stuff. So one of the things is, and I'm going to paraphrase this because I do not want to write it all. One theorem is that there exists a fundamental set of solutions for all homogeneous, linear, nth order DEs, which I will now be abbreviating all of this as HL node. Actually, let me take that apart for yourself. That makes it look weird. For all homogeneous, linear, nth order differential equations. Pretty cool. So that kind of makes sense. You would expect that to be the case, that if you have a second order, it should have two solutions as its fundamental set of solutions. So it kind of makes sense, but it's good to see that nonetheless. So let's see now. Now we're going to have some of the payoff for establishing this. Okay, so I think I need to. I'm going to have to write a lot. Bear with me. New theorem. Here we go. Let y1, y2, dot, 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 y sub n be a fundamental set of solutions of a homogeneous linear nth order DE HL node on interval I. Okay? Then, here we go. Monster big. The general solution, written big, underline, of the equation is, ready? Y equals C1, Y1 plus C2, Y2 plus dot 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 C sub n, Y sub n, where C1, C2, dot dot dot, Cn are arbitrary constants. Okay? But wait, what does that mean? That they're arbitrary constants. These are just constants. Have we seen anything where we were able to, gosh, I guess this is a little bit of a stretch, but have we seen anything recently where I was able to put an arbitrary constant in front of something and make it equal another thing? Do you remember? Yeah, that's the way that we were able to tell if something was linearly dependent. If I can form the third solution by some linear combination, then we had that it was dependent. But in this case, what I want you to take away from it is the general solution boxed in with stars, because this is insanely important what we're about to say, is a linear combination of the fundamental set of solutions. The general solution is a linear combination of the fundamental set of solutions. Okay? Now, let's look at some examples to really drill this home. Here we go. Let's let y is equal to e to the 3x and y is equal to e to the negative 3x. Okay? And we're going to say these are solutions of the HL node. In this case, it's going to be an HL2-ode since it's a second order. But y double prime minus 9y equals 0. It's homogeneous. It's second order. Two solutions. Okay? If we want to verify that they are linearly independent, we can do that. I can look at them and tell there's no way I'm making e to the 3x out of the e to the negative 3x and vice versa. So I know they need to be linearly independent, but I'm going to run the Wronskian anyways. It's just, since it's a second order, it's really easy. So e to the 3x, e to the negative 3x, and then 3e to the 3x and negative 3e to the 3x. So it's going to be this one. So negative 3e to the 3x plus 3x is 6x minus this times this, which is 3e to the 0, right? So I'm going to wind up with, wait, did I miss my negative? That's a negative. That should have been a 0. I was going, wait a second, I'm wrong. No. You saw nothing. So this is negative 3 minus 3, which is, because e to the 0 is 1, negative 6. what values of x will make that equal to 0? There are no values of x that would make that equal to 0, so they are linearly independent. Since they are linearly independent solutions of this second order equation, I can now say, here we go, y equals c1 e to the 3x plus c2 e to the negative 3x. This is the general solution. Isn't that amazing? I really hope that, I'm, at least a few of y'all are like, oh, that's amazing, I've never seen that before. But this is so important. We just took two solutions for our second order differential equation. We verified that they were linearly independent. Therefore, they are a fundamental set of solutions, and the general solution can be formed by the linear combination of the two solutions. That is so big. Now, I'm going to go one step further than what your book says and say, what we just did is we just found the general solution for the differential equation. This is the general solution, okay? This is not a general solution. This is the general solution. All the work that we've done up to now has been to show that we have a unique set of solutions based on our initial conditions. If we have that, then we can say that once we find one solution and we find the other solution, we can then say if they are linearly independent, using the Wronskian, I can now form the general solution for this differential equation. Okay? I can't stress how big that is, what we just did. There isn't another one lurking in the wings. There isn't a better way to phrase this or do anything like that. There may be different forms that this can take. Of course, you could always write exponentials as sines and cosines, but this is it when you get right down to it. We have our two solutions. They're linearly independent. Therefore, the general solution is just the linear combination of the two. Boom. Alrighty, I'm going to beat the dead horse one more time, just because I like to be super thorough with stuff that's important. For this one, let's say that we have y1 is equal to e to the x, y2 is equal to e to the 2x, and can you guess what y3 might be equal to? E to the 3x, yep. Let's say they're solutions of y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Alrighty? So, are they linearly independent? They may not look like it at first glance, but there's no way I can form e to the 2x or e to the 3x using e to the x. It can't happen. So, I suspect the Wronskian should work out to not equal 0. So, e to the x, e to the 2x, e to the 3x. Then we're going to have e to the x, 2e to the x, 2x, 3e to the 3x, e to the x, 4e to the 2x, 9e to the 3x. Alrighty, so it seems like it's going to be a lot, but it's really not. I'm going to wind up with e to the x times this times this. Well, I'm going to wind up with 5x is going to be my exponent. 18 minus 12 is going to be 6 e to the 5x minus e to the 2x times, again, now I'm going to have 4x for my exponent, 9 minus 3, 6 e to the 4x plus e to the 3x times e to the, so it's going to be the 3x is going to be the exponent, so 4 minus 2, 2e to the 3x. Well, what is that going to give me? 6e to the 6x minus 6e to the 6x plus 2e to the 6x. These two cancel. I'm left with 2e to the 6x. There's no value of x that I can put in here that will make this equal to 0, so they are linearly independent. Okay? So, box off right here since I ran out of room down there. The general solution is y equals c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Boom. That's the general solution to that system. Isn't that beautiful? Alrighty, so let's clear it. And that's the first big thing to take away. And now we can move from there into some new territory. So let me clear this and we will get started on the next stuff. Okay, so we've been talking a lot about homogeneous equations. Now let's talk about non-homogeneous equations. Okay, so here we go. This is something that we already sort of know, but let's write it out in explicit detail because we're going to use it in just a second. So any function y sub p that satisfies the non-homogeneous equation and it's going to be something like a sub n of x d the nth derivative of y with respect to x plus dot 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 all the way down to a naught of x times y equals g of x, where g of x is not equal to 0. Okay, so g of x is not equal to 0. So any function y of p that satisfies this non-homogeneous equation is said to be a particular solution. Okay? Now, we've been using particular solution for a while now, kind of informally, but this is to kind of really nail it down. And from here on, when we say particular solution, we mean one that solves a non-homogeneous equation where g of x is not equal to 0. Okay? As an example, let's say I had y double prime plus 9y equals 27. Okay? Y sub p could equal 3. Second derivative of 3 is 0, plus 9 times 3 is 27. 27 equals 27. Yep, that works. So this is a particular solution right there. Alrighty. Now, that's okay, big deal, but we're going to be using it in this form from here on. Particular solution means a solution to the non-homogeneous differential equation, not homogeneous, non-homogeneous, okay? So what we're about to say is among the most important things I'm going to say all semester, so pay super close attention to it. If y1, y2, dot, 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 all the way up to y sub n are solutions of a homogeneous linear nth order differential equation on I and y sub p is any solution of a non-homogeneous linear nth order differential equation. So notice this is the non-homogeneous, this is the homogeneous. Then the linear combination and what is it going to look like? Well, it's going to be y equals c1 y1 plus c2 y2 plus dot 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 cn yn plus y sub p is also a solution of the non-homogeneous equation. Okay? Now, this is kind of a simplification because this implies that this is the homogeneous equation. This is the non-homogeneous equation that is the homogeneous equation equal to something that's not zero. So this HL node and this HL node are the same. It just has an n after it, which means there's something that it's equal to or not equal to zero, I guess is a good way to put it. Then I can have a linear combination of arbitrary constants in front of my my linearly independent solutions for the homogeneous part, plus a particular solution that fits the non-homogeneous part. Okay, let me show you what I'm talking about. Okay, so that was the kind of hand wavy. Now let's go into the kind of, you know what, I think I'm going to restate this in a nicer way. I think I can make it sound even better. I'm going off book here, so bear with me. Okay. Y equals C1 Y1 plus C2 Y2 plus dot 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 C sub n Y sub n. Okay. Now, this right here is called the that's wrong kind of complement. Complementary solution. Okay. So, what is this? This is the solution for my dE, my stuff, equal to 0. Okay. That's what this is. It is the solution, the general solution to whatever my dE is that is equal to 0, that is homogeneous. Okay? Now, y sub p is my particular solution. Okay? That is going to be the solution to the dE equal to g of x, where g of x is not equal to 0. Okay? Here we go. Drum roll. I think I can put it in right here. The general solution, I think I can squeeze it in. the general solution of the non-homogeneous linear nth order dE is y equals the complementary solution plus the particular solution. Can I squeeze it? Yes. Okay. So the general solution of a non-homogeneous differential equation is the complementary solution for the homogeneous part, where if I set this dE that originally is equal to g of x, if I set it equal to 0 and solve, that is going to be the complementary solution plus the particular solution that pops out when it's equal to g of x. Okay? So, here's a quick example. I think it will all make sense. Please burn this into your brain though. The general solution of a non-homogeneous linear nth order dE is the solution of the associated homogeneous piece that gives you your complementary solution plus a particular solution that applies for the non-homogeneous part. Okay? So here we go. Clear this and write that out. Gosh, I have such trouble clearing this thing. Here we go. Let's say that we have the following. Y triple prime minus 6y double prime plus 11 y prime minus 6y equals 3x. Okay? This is the equation, the differential equation that we had earlier when we ran the Wronskian. Okay? So, we already proved that y equals e to the x, y equals e to the 2x, and y equals e to the 3x were solutions of y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Okay, that was the associated homogeneous portion. And I'm flipping back to make sure that I wrote that right. Don't want to do this off the top of my head. Yeah. Okay, so the solution, the general solution for the homogeneous version was y equals, what did I have? C1 e to the x plus C2 e to the 2x plus C3 e to the 3x, right? This is the complementary solution, which I am going to denote as y sub c. Y sub c. Okay? Now, if I tell you that y sub p, the particular solution of this non-homogeneous equation, is equal to negative 11/12 minus 1/2 x. Okay? If I say this is the particular solution to the non-homogeneous one, which has 3x at the end, then, here we go, y, the general solution of a non-homogeneous differential equation is y sub c plus y sub p. Okay? So, y, the general solution for this non-homogeneous equation is c1 e to the x plus c2 e to the 2x plus C3 e to the 3x plus negative 11/12 minus 1/2 x. This is the general solution of the non-homogeneous linear nth order DE. So the general solution of a non-homogeneous equation, anything that's not equal to 0, is a combination of the solution to the homogeneous, as if I make this a 0 and solve, plus a particular solution that uses this non-homogeneous part. Okay? We are going to be doing this for the rest of the semester, solving for, well, maybe not every single section, but my goodness, we're going to be doing a lot. We're going to, when given a non-homogeneous equation, solve the associated homogeneous part to get y sub c, and then we're going to solve for y sub p using a variety of techniques. The general solution is then going to be the combination of the two, y sub c plus y sub p. That is the general solution of a non-homogeneous linear nth order differential equation. Alrighty. So, what we're doing for the rest of the semester is working with non-homogeneous stuff. It's not all of it, but it's a lot of it. So we're going to be doing the same thing we've been doing, which is solving homogeneous portions, which those are usually way easier. You can imagine if I'm doing the integrating factor, I suddenly have my f of x equal to 0, which makes the integration really easy at the end. Plus there's some other techniques we can do if it's homogeneous, which we'll learn. But we're going to find the homogeneous solution first. The homogeneous solution, let me rephrase that, the solution of the associated homogeneous. So if I had y triple prime minus 7y equals 5, first thing I'm going to do is solve for y triple prime minus 7y equals 0. That's going to give me my y sub c. That is the worst y ever. I'm going to try that again. My y sub c. Then, after I find my y sub c, I'm going to work with the non-homogeneous part and find y sub p. Then the general solution is going to be y sub c plus y sub p. And that's it. Boom. So, that's it. That's what we're going to be doing for the rest of the time. So, let me see. I don't know if your homework actually makes you do. Let me make sure here. No, we haven't hit that yet. So your homework is going to be to do some, see if given solutions form a fundamental set, and if you can verify that a given solution verifies is the general solution of a non-homogeneous part. So that one's going to be a little bit tricky. So your homework is going to be, let me clear homework. Oh, wow. You can write homework like that. That's really cool looking. I'm going to leave it. So homework is going to be from 4.1. And it's going to be, let's go with 23, 25, and 35. 23, 25 are just simple verification. You're going to take the derivatives and plug them in, see if you get right side equal to left side. 35, though, is not going to be as nice. So just try it out. It's still going to be verification, but it has a few more steps to it after that. Don't spend a lot of time on 35, simply because it's got some pieces to it that we don't want to spend a lot of time on. So just give it a try. If it works, cool. If it doesn't, just wait till the next video and I'll run through it then. Alrighty, good luck with the take home that I just sent out a while back. And if you have any questions, come by and see me during office hours. virtual office hours. All right. Stay safe. Take care. And I am out of here. Bye-bye.